In this video, I want to take a look at how we can represent functions as power series. This is going to be sort of, again, a precursor to talking about Taylor series, where we'll talk really fundamentally about how we can build these things. But I want to talk about some of the bigger ideas and operations that we can apply to power series in order to construct functions out of these things. So just a quick reminder, what is a power series? In general, a power series centered at a given point that we'll call in this case x equals a is given by the following. So we would have a sum from n equals 0 to infinity of some coefficient that we'll just call Cn times x minus a to the n. This is a generic power series centered at a. And so if you looked at the individual terms, when you plugged in n equals 0, we'd get basically c sub 0, and anything raised to the 0th power is just a 1. In fact, we're going to assume even when x is equal to a and this is 0, that 0 to the 0th power, in this case, we will define that to also be 1, even though it's normally undefined. The next term, when n equals 1, would give us c1 times x minus a to the first power. Then we get plus c2 times x minus a squared, and so on and so forth. So again, this assumes that the first term c0 times x minus a to the 0 is equal to simply c0 even when x is equal to a, which would normally make the number inside the parentheses here a 0. So we're going to assume that. Notice that in that case, if x is equal to a, all of these other terms are going to go to 0. That would be 0 to the first power, 0 squared. We'd have a 0 cubed. All of those are just going to be 0, and we would have automatically a result that's converged, and it would just be converged to whatever C0 is. So notice that anytime, basically every time, let's do it this way, that every term is 0, every other term And so let me just highlight that caveat I mentioned a minute ago here with a little note that about the C0 term. So this assumes that C0 times x minus a to the 0 will be equal to C0. So basically that this term, x minus a to the 0, is going to be 1 even if x is equal to a, which would make the number inside of here be 0. So basically we're saying the 0 to the 0th power, we're going to define that to be 1. However, if x is equal to a, so also if x equals a, then every other term is 0, meaning this term would be a 0 to the first power, and I'd get 0 contribution from this term. This would be a 0, so I'd have 0 squared, and this would give me no contribution. Then I'd have a 0 cubed, and a 0 to the 4th, and so on. All those other terms would be 0. What this means is that in the case where x is equal to a, we are converged at least that one point. I'd have C0 plus a whole bunch of other zeros. This means the power series converges at least at the point x equals a. And it, in fact, converges to the value of C0. Okay, so basically, again, what I'm saying is no matter what, this had to do with the idea of a radius of convergence, we're always going to have our power series be accurate at least at the one point that we're centering the power series on. It's always going to be accurate at x equals a, even if the radius of convergence is 0. It'll still pass through the one point that we're interested in. Okay, so the hope is to use a power series to represent different functions. And I want to look at one example way back from section 11.2 where we already did this. So we already represented some functions as power series. And one of them we did way back in 11.2. So this is from 11.2. So recall that we found in section 11.2 the following, that the sum from n equals 0 to infinity of basically x to the nth power, which looks like if we plug in n equals 0, we'd get 1. N equals 1 is x, plus n equals 2 is x squared, plus x cubed, plus so on and so forth. This wound up being equal to 1 over 1 minus x. This converged whenever the absolute value of x is less than 1. What this came from was basically a geometric series. So this right here was, to remind you, a geometric series with what we normally called a being equal to 1 and what we normally called r being equal to x. And we had a result of what it converged to. It converges to a over 1 minus r. So a is 1, 1 minus r in this case is now 1 minus x. So this is the idea. This is a geometric series with these properties. This is what it converges to. It only converges as long as our r is less than 1, or in this case, the absolute value, of r is less than 1. In this case, because r is x, here's the condition that we have. So it turns out we have a way to write this function, at least over this interval from -1 to 1, as a power series. We have found a way to write 1 over 1 minus x as a power series. But again, only on the interval, and I guess I don't need this in parentheses, on the interval from -1 to 1. So this representation isn't valid everywhere, it's only valid over that interval. Okay, so it turns out that we can do this for a whole bunch of other functions, and one way that we can develop what some of these other functions are by just modifying this one. So we can modify this representation to find others. So there are a couple of things that we can do. And so let me just go through a short list of some of the operations that we're going to be using. So we have some operations that are going to make life a lot easier for us. So what I'm going to do is I'm going to let f of x have a representation that looks like this. If we have f of x being represented with a power series that looks like this, a sub n x to the n. And again, I'm going to start leaving off the indexes here just because who cares. And let's just say, and we also have a second one, because it might be nice to talk about how we can combine things. So maybe I have a second one that looks like b sub n x to the n. Then we have the following properties. Number one, or operations, I should say. What happens if I do f of some constant times x? So basically what I'm saying is, what if instead of having x, I replace it with k times x? What happens when you put a constant in? Well, what would happen is basically we would replace everywhere that x showed up with a k times x. So I would, in this case, get the sum of a sub n kx to the n. And when we actually write that out, that means I'd get a k to the power n and an x to the power n showing up in that term. So this is what that would look like. What happens if I replace, if we have some f of x, and it's being raised to some power, and let me call the power capital N, because we've already used lowercase n as our index that we're summing over. So let's say that I have x raised to some power called capital N. What is that going to look like? Well, in this case, same thing. I just need to replace everywhere that x showed up here. I need to replace it with x to the n. This passes through. So we will get a sub n times x to the capital N raised to the lowercase n. And if we simplify this, this is simply x to the, when you have a number raised to a power, and then raise that again to a power, you multiply the powers together. So this is simply n times n, lowercase n times capital N. A third property, or third operation, is if I combine my two functions, and let's say plus or minus, I can add them or subtract them, I can simply add or subtract the two series as well. And on top of this, we're also going to have some rules about how differentiation and integration work as well. So I'll do those as well, but let me just put this down here. We'll go into more detail in a minute, but let me just say integration and differentiation work as well under certain assumptions. And we also already used this property that integration and differentiation work back in the last video when I looked at a power series that wound up being cosine, and we took some derivatives to see how that all worked out. So these work as well, and we'll see more of this later. So under certain assumptions. So we'll come back to this one in a minute. But for now, I want to use these first few properties here to look at another example. So, for example, we just said that we know that if I have f of x equals 1 over 1 minus x, that is also going to be equal to, or that this has a power series representation and again, this comes from the geometric series of the following, that this f of x is equal to 1 plus x squared plus x cubed plus dot dot dot, which if we write that out, it's the sum from n equals 0 to infinity of x to the nth power. And again, this all assumes that the absolute value of x is less than 1. So we know that this is true, that if this is the f of x that we're interested in, here's its power series representation. What if we want to now write a new one? Let's call some new one g of x, which is going to be equal to, let's say, 1 over 1 plus x squared. I want to write this as a power series. Well, how can we do that? Well, according to these properties up here, if I notice that the difference between these two is that I've basically just modified what this term in the bottom right looks like. Over here I have 1 over 1 minus x. Here I have 1 over 1 plus x squared, which I could rewrite as 1 over 1 minus, putting it all in parentheses, a negative x squared. This mirrors the format that I put this one in, 1 over 1 minus x. And all I've done is replaced 1 over 1 minus some stuff. I've replaced what appeared as x here with a negative x squared. Essentially, I've taken x and I've raised it to a power, exactly as we've done here, so this property will apply. I'll be able to basically go into our power series here and replace everywhere that x showed up in this one. I can replace it with x to the n, in this case x squared. Similarly, the negative sign here, that's just multiplying by a constant, and the same thing is true. I can just figure out basically that I'm going to have a negative 1 raised to the power of n that shows up in here. So basically that's all we need to do. We just need to replace x in 1 over 1 minus x with a negative x squared. And what that will tell me is that basically if I want 1 over 1 plus x squared, it's going to be equal to, well, we look at the power series representation of the original function, and everywhere that x shows up, we replace it with a negative x squared. So the first one I'm going to have 1 plus, well, there's an x, so that needs to be replaced with a negative x squared. Then I have an x squared, so plus a negative x squared squared plus negative x squared cubed. And all I've done is taken each one of these x's and replace it with a negative x squared plus dot dot dot. And this should give me the power series according to these properties here, that basically the constant's going to sift through exactly like this. The power will just also sift through exactly like this, and we can basically replace x with one of these other terms or a combination thereof to get something that looks like this. So that 1 is still going to be 1. This term is going to simplify to simply being a negative x squared. This one I'm squaring the whole thing, so the negative sign will become back to positive, and I'm going to get x to the 4th, so I'm going to get plus x to the 4th. The next term is cubed, so the negative sign, I got a negative 1 cubed, that's still going to be negative, and I'm going to get x to the 6th, and then back to a positive for the next term, and so on and so forth. Similarly, we can basically go and swap in to the original formula over, where am I looking? Over here. I can basically go and just replace the x that showed up here with a negative x squared. So this thing should be equal to the original formula that we had from n equals 0 to infinity of x to the n, but I just need to replace that with negative x squared. And that will generate this exact list of terms that we've got right here. So if you wanted to clean this up, you could write this as the sum from n equals 0 to infinity. Let's separate the negative 1 out to make it clear that it's going to be an alternating series. I have a negative 1 to the n, and then I have times x to the 2n. So this is equivalent to this, just separating the negative 1 portion and the x squared portion, each of them to the nth power, separating them out like this. So here's a generic representation of this particular function. And again, it's going to have the same restrictions though. The old one only worked when the absolute value of x was less than 1. Just like I had to replace all of the terms in here where x showed up with negative x squared, I also need to do that same thing in the condition. So the condition is the following. Oops. With the modified condition, it used to be the absolute value of x was less than 1. Well, now I need to come back and erase that x and put in negative x squared. Replace everywhere that x shows up, including in there, replace that with what we're looking for here. And luckily in this case, negative x squared, inside our absolute values, the negative sign has no bearing. So this is going to imply simply that the absolute value of x squared is less than 1. And if we're squaring the x squared term here, basically, this whole thing means that all I care about is simplifying. This is the same thing as saying that absolute value of x is less than 1. It's really the same thing, right? If x is greater than 1, then x squared would be greater than 1. If x is less than 1, then x squared would be less than 1. So if 1 is our cutoff here for x squared, it's also the cutoff for x. They have the same relationship. And so we wind up in this case with the same condition. And we have the same condition because this is still a geometric series with just a different argument being plugged into it, essentially. So that is the idea. So this is going to be a common thing that we can do. Take a known power series and its representation and wholesale swap out the argument x with some new term. And if we do that uniformly across everything, we can change the form of the function, again, using a combination of these operations up here. Similarly, we can do the same thing with integration and differentiation. If I know what a function looks like and its power series representation, then I can figure out a new function, the derivative f prime of x. If I know what the derivative of this looks like, I can find the derivative of the power series to get its representation as well. So let's see an example of that. But before we do that, I want to be a little bit more careful writing about how we apply integration and differentiation. So let's talk a little bit more about integration and differentiation. Okay, so if our power series, written generically as the one that we just wrote, so some sum of some constant x minus a to the n, and again, notice I'm dropping the labels on the sum here. Doesn't matter if you're starting at n equals 0 or n equals 1, whatever. But if this has basically convergence on a certain interval, on a radius of convergence that's greater than 0. So if this converges with a non-trivial interval, where we actually at least have some range of values, then basically, then so do its integrals and derivatives. So this is sort of the long of the short of it. And we can take these, again, normally. Let me put that into words here, which we can compute normally. On a term-by-term basis. Or if we're careful, we can compute on sort of the generic representation that looks something like this. We just always have to be very careful with the indexing and what that means. Okay, so in this case, let's find a series representation, a power series representation for one of the following. So find the power series representation of, let's say, 1 over x minus 1 quantity squared. So if I can relate this function to a known function through either integration or differentiation, then I can use that to generate the power series for this. So I'm going to start with 1 over 1 minus x, which we know is equal to 1 plus x squared plus x cubed plus dot dot dot. We already have the generic representation. This is the sum from n equals 0 to infinity of x to the n, with the condition that the absolute value of x must be less than 1. Okay, how does this function relate to this function? Well, it turns out that these two are going to be related through differentiation. So let's think about what is. So now let's take the derivative. So I'm going to take d dx of 1 over 1 minus x. What is the derivative of that? If you want, you can think of this as simply the derivative of 1 minus x to the negative 1 power. So maybe that's an easier way to see it. We can do power rule on this thing. So it's the derivative of 1 minus x to the negative 1 power. So we can basically do a u substitution on here. Or I guess that would be for integration. We can basically just do chain rule on here. I'm going to have stuff to the negative 1 power. So what's the derivative of stuff to the negative 1 power? Well, the negative 1 will come down, and the whole thing will go to the negative 2 power. So I'll have negative 1 minus x to the negative 2 power times the derivative of the stuff. So times the derivative of what's in the parentheses, which is going to be an extra factor of negative 1. And so this is going to wind up giving me this negative 1 will cancel with this negative 1, and I'll wind up with 1 over 1 minus x squared. And that may look a little bit different, but remember, because we're squaring it, what I've got up here, these are actually equivalent because it's getting squared down here. Essentially what I'm saying is you could factor out a negative 1 squared. So let's just do that just to make it totally clear. This is the same as 1 over, I could write this as negative x minus 1, whole thing squared, right? I've forced a negative 1 sign out of this, but because we're squaring it, it doesn't make any difference. When I apply this square, this is the same as having the negative 1 squared and the x minus 1 squared, but this is just going to be 1, and we wind up with 1 over x minus 1 quantity squared. So basically, I'm saying that this is the same thing as this, and I just kind of showed how you can factor out that negative 1 to show that they're equivalent, but these two things are the exact same thing. So we can now apply the derivative to the power series of the original. What I'm saying is if we have d dx of 1 over 1 minus x, that's going to be the same as d dx of its power series representation, which was 1 plus x squared plus x cubed, and so on. We already showed that this derivative was the exact same thing we're looking for, so 1 over x minus 1 squared. And what is this derivative going to be? Well, what's the derivative of the 1? That's a 0. What's the derivative of the x? That's a 1. What's the derivative of the x squared? That's going to be plus 2x. What about the x cubed? That's going to be plus 3x squared plus dot dot dot. So I now have this representation, which we will notice if we want to write this, we have a couple of options. If I want to figure out what this looks like, written as a sum. I want to write it as, basically we've got a couple of options. We can ignore this first term because that 0 being added to the sum isn't going to do anything. So let's try this. I want to start my index at 0, go to infinity, but I can forget this term because it doesn't contribute anything. So I want when n equals 0, I want that to spit out this term for me. So that just means, if I look at the pattern, that if this is my n equals first term, and this is the second term, and this is the third term, the coefficient that we've got right here is equivalent to basically n, rather, plus 1. So I guess I should say this is the 0th term, the first term, and the second term. So each number that we got here is n plus 1. Ooh. Let's go back in there. So the coefficient is n plus 1. And then the power is, this is x to the 0th power because it's a constant. Here's x to the first power. Here's x squared. So the powers are just the values of n. So here's what we've got. This is what we're looking at. Incidentally, what would have happened if I just took the original power series representation of this and took its derivative? So what I'm suggesting is, what if I took d dx directly of the power series representation in its shortened form here? So if I took the derivative of n equals 0 to infinity of x to the n, what would happen there? Will I get the same thing as I've got here? The answer is yes, we certainly should. The x, the derivative just applies, right? Because this is just a sum of a bunch of terms. The derivative goes and applies to the actual terms. We can sift that derivative onto the inside of the sum. So this is really just the sum from n equals 0 to infinity of the derivative of a bunch of x to the n terms. So, and again, we just need to be careful about the indexing, because in this case, there's one term that we need to keep in mind. When n equals 0, this x to the 0, it's really a constant. And the derivative of a constant is going to be the 0 that we got over here. So you can't really treat that one with power rule in the same way that you might normally. But what does this look like? This looks like, when we take the derivative of x to the n, you get n x to the n minus 1. And all we've done is basically said, okay, this doesn't work when the index down here is 0, right? So this is an incorrect index down here. It's only going to work when this index starts at a 1 here. So when you take the derivative, again, of this term by itself, you need to be really careful about that first term. In fact, a lot of the times it's better to actually, maybe a more careful way to write this would be down here. So I can kind of do this as an aside. What I really want to think about this is writing it as 1 plus, so that's when n equals 0, right? When n equals 0, we get a constant. The rest of the terms depend on x. The rest of the terms will follow power rule, but the 1 is a constant, has a different approach that we take. So this is really the sum from n equals 1 to infinity now of x to the n. And we dealt with that first x to the 0th term separately. And so if I'm taking the derivative of this instead, let me put it in parentheses here and write that derivative in front of it. Now you can see the derivative of that first term is going to just be 0. And now it'll be a little bit more clear why the index gets preserved. It's going to be n equals 1 to infinity of, again, nx to the n minus 1. And so this is really where we get this, but you can also just make the argument after the fact that this needs to be reindexed to 1. Are these the same? So these two different representations, are they the same? And the answer is yes. Again, if I go back and now just reindex this to 0. So let's compare. I have the sum from n equals 0 to infinity of n plus 1 x to the n, and the other one I have the sum from n equals 1 to infinity of n x to the n minus 1. And essentially all we've done is basically shift both of these, right? This is one larger than what's up here. Same thing here. This is one larger than what's up here. But this whole term up here is one larger than what's down here, but the index down here starts one before this one, or one after this one, to kind of account for that. So you can verify in both cases the first term that this one's going to spit out is the coefficient will be 1 times x to the 0. Same thing, when I plug in n equals 1, the coefficient will be 1 times x to the 0. And so these two things are equivalent. They will produce the same values. And it just depends on if you want to keep your sum 0 indexed or 1 indexed. Where do you want to start as your first term? But these will both spit out for the first term. Plugging in n equals 0 up here, I'll get 1 times x to the 0, which is just 1. Down here, I'll get 1 times x to the 0, which is just 1. Then for the next term, when n equals 1 up here, I'll get 2 times x to the first, so plus 2x. Down here for the second term down here is when n equals 2, I'll get 2 times x to the 2 minus 1, which is 1, so 2 times x to the first, and so on. And you'll see that they will wind up giving me the exact same list of terms in both cases. Two different ways to write the same series, one starting at an index of 1, one starting at an index of 0. And I won't really care which you use. Typically on the homework, they will specify start at an index of 0 or something like that. They will tell you where you should be indexing your power series from. Okay, hopefully that makes some sense. Let's try another example, kind of related to this. I want to basically evaluate, let's see if this will work, the integral of x over 1 minus x to the 8th power dx. And I want to do it as a power series. And while we're at it, let's find the radius of convergence that makes this thing accurate. So I'm going to break this up into a few different pieces. So I'm going to come back again to our properties up here and just think about what we're allowed to do. One thing that wasn't explicitly made clear here is what happens if I were to say change it so that I added an extra factor of x. So basically what I'm suggesting is, as an additional property, what if I did this? What if I wanted x, f of x? If this is how f of x is defined, what would happen if I did an x in front of it? Well, it turns out this is totally allowed as well. So that would be x times its power series representation, which is the sum of a sub n x to the n. But I can totally put that x inside, right? This is just a big long sum. And so essentially this is just a distributive property. If you think of the sum as being in parentheses, we have some big long sum of terms and we've factored an x out of it, you can distribute that x through to all the terms. And you would wind up with the sum of an x to the n plus 1. They all get an extra factor of x. So that's kind of the property that I want to use down here. And I want to rewrite this as basically the integral of x times 1 over 1 minus x to the 8th dx. So in this case, essentially what we're arguing is that this is the same as x. And again, we're trying to find the integral. So let me just do this as a side note again, and then we'll come back to the actual computations here. So all I'm trying to note is that basically our x over 1 minus x to the 8th is the same thing as x times 1 over 1 minus x to the 8th. And that 1 over 1 minus x to the 8th, we can represent that as a power series. So I have got my x that's factored out, and the power series looks exactly like the one we had for 1 over 1 minus x. Right? And we're basically just doing this again. So if I had the one for 1 over 1 minus x, and I replaced the x with a negative x squared, then I could get the power series representation of this piece. Doing the same thing down here. All I'm doing is swapping out what we used to call x, and now it's x to the 8th. And so what used to be 1 plus x squared, and so on, is now going to be 1 plus x to the 8th plus x to the 8th squared plus x to the 8th cubed plus dot dot dot. Let me zoom in so I can actually write a little more clearly here. Those are a little ugly, but hopefully kind of readable. Turns out my handwriting's not very good when I zoom out. So let's try to write that a little more clearly. So x to the 8th squared, x to the 8th cubed, and so on. So this is what we're looking at. You can think of this power series representation as looking like this. What is that equivalent to? Well, that's going to be simply the sum from n equals 0 to infinity of, we have a factor of x times our x to the 8th to the nth. Right? That's what this thing winds up looking like. Okay, so again, that x can be distributed in, or it can be pulled out, because this x has absolutely no bearing, or there's no bearing on n whatsoever. This sum has to do with n. As far as n is concerned, this x is a constant. I can pull it outside. So we can either leave it in or pull it outside. I'm leaving it in. We can rewrite this whole thing as the sum from n equals 0 to infinity of simplifying this. This is going to be x to the 8n, but I have an extra factor of x, so I'm going to get x to the 8n plus 1 power. So this is the power series representation of this. And now what do we want to do? We want to integrate. So if we want to integrate this, all we need to do is integrate the power series representation. So I'm going to do the integral of the sum from n equals 0 to infinity of x to the 8n plus 1. And again, we're doing this all with respect to x. So first things first, whenever we integrate, this is an indefinite integral, we're going to wind up picking up an extra factor of c, a constant. So let me just put that out in front just to make it clear that it's not going to be part of the sum. So we get a constant plus the sum from n equals 0 to infinity of, what is this integral going to look like? So if you have x raised to some power, when you integrate it, the power increases by 1, and then you need to divide by whatever that value is. So for example, right, if I have x squared and I'm integrating that, remember that it's going to go up to an x cubed, but then I need to divide by 3 to account for that as well. And so what I'm suggesting here is this power is going to raise by 1. It's going to become x to the 8n plus 2, but then I need to divide by 8n plus 2. So that's just our power rule for integration. Just put it in parentheses there. So that is what the integral of the original function looks like, written as a power series. Now let's think about the idea of convergence. So what were the steps here? Let's just think about what we did. The first thing is find a way to relate the function that we're dealing with to a known function. The only known function we have right now is 1 over 1 minus x. 1 over 1 minus x is all we've got right now. So in this case, I see that this looks kind of similar to that. If I factor an x out, then I have x times 1 over 1 minus x to the 8th, but this x to the 8th is the same as just replacing the x in the original function, 1 over 1 minus x, with an x to the 8th. And I know the power series representation of 1 over 1 minus x, so I can construct the power series representation of 1 over 1 minus x to the 8th. So that's how we got all of this. So the first thing is relate the function, in this case the integrand, to a known function, and come up with a power series representation. That's what we've done here. Next step would be to actually carry out the integration. We've carried out the integration on this known power series representation that we were able to come up with. And we got this. And the last step is to now figure out where this is valid. I know the original function that we started with, 1 over 1 minus x, its power series representation only converges between -1 and 1. Basically, that is to say its radius of convergence is 1. It's centered at 0 with a radius of convergence of 1. So how is this one going to work? This series, if I look at this, the series 1 over 1 minus x to the 8th, that part converges basically whenever the absolute value of x to the 8th is less than 1, right? All we did was, this was what we used to call x, we swap it in, that's what we used to call x. So that's how we do it, just swap it right in. This is from the geometric series, but this, if you think about x to the 8th, the way that that works is basically if the absolute value of x to the 8th is less than 1, take your 8th root of both sides. This is the exact same thing as simply saying absolute value of x less than 1. Same idea. So this part converges whenever the absolute value of x is less than 1. That's the only part that we need to converge, because this piece, remember, is totally valid to move outside. We could pull that x out. So the whole thing is going to converge. So x times the sum from n equals 0 to infinity of 1 over 1 minus x to the 8th has a radius of convergence of 1, right? All we need is the absolute value of x to be less than 1. The fact that I pulled this x out in front has no bearing on the series itself. So the x has no effect. That x that was factored out has no bearing on the convergence, because it's not part of the original sum that we cared about. So that's kind of the way that we can do this whole thing. So the radius of convergence is still 1. It's still going to converge between -1 and 1. But the 3 steps are to find find a known function that looks similar, find a way to represent the series of that known function, and then rewrite the given function in terms of that representation, as we've done here, do the actual integration, and then go back and do the same thing, relate the idea of convergence of the known function to the convergence of this new function, keeping in mind that we may be able to pull parts of the function outside of the actual series, factor them out. So it's a lot, but hopefully this will become more intuitive as you do more examples. So this is what we've got so far. I want to consider another thing to think about. So this is related, but not necessarily a part of this problem. consider the fact that we know what the integral of 1 over 1 minus x is, right? I can just do this integration. This integral is going to be, again, this would be a u substitution. We'd let u be equal to, let me just do it. We'd let u be equal to 1 minus x. That means du is going to be negative dx. And that means I could rewrite this as basically integral of 1 over 1 minus x times negative dx. And to account for the negative sign I've introduced there, I'd need to pull another negative sign outside. In terms of u, this is now equal to negative the integral of 1 over u du. And what is that equal to when we do our integration? Well, I'll keep my negative sign and I'll get the natural log of the absolute value of u. But going back and plus c, going back and replacing what u is with our 1 minus x, we get the negative natural log of the absolute value of 1 minus x. Again, plus our constant c. Okay, so it turns out that as long as our absolute value of x is less than 1, where the series representation is valid, then it turns out we have a representation that relates to natural log now. We have that negative natural log of the absolute value of, in fact, I can just write it this way. Keep this in mind. So let's think about what we're doing here. If the absolute value of x is less than 1, what does that mean in here? That means that this term is going to be less than 1, which means the term inside our absolute values is going to be positive. Basically, the biggest value that this can be is a little bit less than 1. And when I plug in a number a little bit less than 1 here, I'm still going to get a positive result here. So I can drop the absolute value signs, and I can say that this thing can just be the natural log of 1 minus x. And again, let's just say, let's let c be equal to 0 for this case. I'm just letting it be 0. Okay, to make life easy. So, if 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus dot dot dot, as long as, again, the absolute value of x is less than 1, then the integral of 1 over 1 minus x dx is going to be the integral of 1 plus x squared plus x cubed plus dot 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 dx, which is equal to, when we do that integration, the integral of the 1 is going to become an x. The integral of the x will be a 1/2 x squared. The 2 will be a 1/3 x cubed. The x cubed will become a 1/4 x to the 4th plus dot dot dot. So that's actually carrying out that integration. And we know that that is equal to, we already found the integral of 1 over 1 minus x. As long as the absolute value of x is less than 1, it's equivalent to this. And so we were able to represent the natural log function, natural log of 1 minus x, as a power series. All I need to do is take into account the minus sign. This gives us another power series. If I want the natural log of 1 minus x, so basically the whole thing but without a negative sign, it's equal to this whole thing with a negative sign. So negative x minus 1/2 x squared minus 1/3 x cubed minus 1/4 x to the 4th minus dot dot dot. And we can try to come up with a closed form representation of this if you want. But basically, I have another power series representation. These two things, so we basically have two sort of base functions that you can think of with known power series. the first one, 1 over 1 minus x, was equal to 1 plus x squared plus x cubed, this one that we've been doing a million times. And now we have a new one. Natural log of 1 minus x is equal to negative x minus 1/2 x squared minus 1/3 x cubed minus 1/4 x to the 4th, and so on. And again, if we want to write the closed form versions of these, this is the sum from n equals 0 to infinity of x to the n. And for this one, let's just start it at n equals 1. I think that'll be an easier way to write it. I'm not sure if the book indexes this at 0 or at 1. But notice they all have negative signs. So we'll have a negative sign in here. We have x raised to the whatever power of n is. So if this is the first term, second term, third term, fourth term, we have x to the n again. And then we're also dividing in the denominator here. We're dividing by whatever n is. And so there's a representation for this natural log function. Both of these, again, assume that the absolute value of x is less than 1. Absolute value of x is less than 1. So let me just erase these little indexes down here and box these. These are two useful power series that we now know based on the given properties. Okay. Let me do one more big ugly example that we can use. But again, the whole point of this section is if you know one or two known power series, you can use those operations that we defined above to modify them to kind of expand the usefulness to a whole bunch of additional functions. And that's what I want to do one more time in this last example. So in this last example, I want to find the power series, given the ones that we already know. Find the power series for, let's say our f of x is equal to 2x minus 4 over x squared minus 4x plus 3, a big ugly one. Okay, one thing I want to notice is that we can factor the denominator of this a little bit here, so I can rewrite this as, in fact, we could factor the whole thing, it doesn't really matter, but I'll leave this as 2x minus 4 on top, but we could write it as 2 times x minus 2 if we wanted to. But the denominator factors, two numbers that multiply to give me 3, add to give me a negative 4, are going to be x minus 1 times x minus 3. So here's an algebraically equivalent form of our f of x. This doesn't look very close to what we've got right here, but if I split this up and I use partial fractions to basically rewrite this as the sum or difference of two separate something over x minus 1 and something over x minus 3, then I'll have two different pieces that look a lot like this one. And so that's what I want to use. So make this look like 1 over 1 minus x as much as possible. And to do that, we're going to do partial fractions. We'll get a couple of terms that look kind of like that. So if we've got 2x minus 4 over x minus 1 times x minus 3, I want to be able to rewrite this as something over the x minus 1 plus something else over the x minus 3. And this will work, again, because I've got two non-repeated linear factors in the denominator here. So this is the appropriate form. So if we were to go find a common denominator, I'd need to multiply this one by x minus 3 over x minus 3, this one times x minus 1 over x minus 1, and then we'd look at the numerators, and the numerators on the left would still be 2x minus 4, and on the right I'd have a times x minus 3 plus b times x minus 1. We need to solve for a and b. The easiest way to do that is plug in some values. So let's plug in x equals 1. When I plug in x equals 1 on the left, I will get 2 minus 4, which is negative 2. And plugging in the 1 over here, I'll get a times a negative 2. So negative 2a. And plugging it into here, I will get 0. And this tells me that a must be equal to 1. When I plug in the other value, x equals 3, designed to kill off this term, then on the left, when I plug in 3, I'll get, so 2 times 3 is 6, minus 4 is going to be positive 2. And this will give me a 0 for the first term when I plug in 3, and this one will become b times, again, 3 minus 1 is 2, so plus 2b. And that tells me that it turns out in this case, b is also equal to 1. And so we have something that's really quite straightforward. Our f of x that we originally wrote like this, and then wrote in the factored form, can be rewritten yet again in this form as follows. It's equal to 1 over x minus 1 plus 1 over x minus 3. And these both look an awful lot like what we've got here. We're getting very, very close. So let's see if we can figure out a way to kind of rewrite both of these terms. So again, we're getting closer to 1 over 1 minus x, which is our goal. Okay, so looking at this first term, if I want to rewrite this one, I can just swap the order of these terms and maybe factor out a negative sign. Maybe that would be the easiest thing to do, is factor out a negative 1. So I could write this as a negative 1 over 1 minus x. So by factoring out a negative sign, it switches this one to be negative, this one to be positive, and that negative sign accounts to switch them both back. So this term now looks like this. I've just forced a minus sign out in order to flip both of these terms. And I've got something that looks exactly like what I was going for. So that one's easy. This one's going to be a little bit trickier. I want to do something similar. I want to force out a minus sign. So I'm going to write it as minus 1 over, now it'll be 3 minus x. But I also don't want to have a 3 here. I really need a 1 here. So let me just recopy this first term here. And for the second term, I want to turn this 3 into a 1, which means I need to basically divide this whole thing by 3. And I need to do the same thing top and bottom. So basically what I'm going to do is I'm going to multiply top and bottom by a third. I'll wind up with a third on top, and on the bottom, I'll have a third times 3 minus x. And if we, again, let me copy this one, not touching it yet, but if I distribute this through, then what I've really got is a minus 1/3. I can bring this 1/3 out. I'll have a 1 over, and I'm going to distribute this one through. So I'm going to get 1/3 times 3 is 1, minus a third times x is going to be x over 3. And now I've got something algebraically equivalent to this that looks a lot more like this piece over here. And I can do the substitution method where I basically just replace the x that shows up here with an x over 3. And we've just got a factor of a third sitting out in front of everything. So with all of this in mind, I can basically get the two separate series for this added together. This first one, I'll have a negative sign, and it's going to be the sum from n equals 0 to infinity of x to the n. This was the power series representation of 1 over 1 minus x. For the second one, I'm going to have minus a third sitting out in front of everything, And it's the exact same thing, but everywhere that x showed up in this one, I now need to replace it with x over 3. So this is going to be the sum from n equals 0 to infinity of x over 3 to the n. And that gives us that representation. So if we want, we can even distribute this 3 back into here, and all it will do, we've got minus signs again in front of both of these. We can try to combine this into one big term. That's all I'm trying to do. So I want to turn it all into one big sum. I want to write it as the sum from n equals 0 to infinity of, I can distribute that negative sign on in if we want. So I can write this as just a negative x to the n. Put this in parentheses here. So negative x to the n. And then this negative 1/3 times this term is going to be, so negative 1/3 times x over 3 to the n. Getting close to what I want. But notice they both are going to have an x to the n, x to the n. So I'd like to factor that out as well and just see if I can get a coefficient in front of this whole thing. And that's what we're going to wind up with here. So the last step, n equals 0. And at this point, again, we're just playing an algebra game. We came up with the series representation as soon as we got to this step. We're just trying to clean up that series representation, power series representation, so that it's a little bit easier to understand or write out the terms of. So what I'm saying is, I've got an x to the n here, x to the n here. So let's assume that we factored out the x to the n. What is the corresponding coefficient? Well, I have a negative 1 minus, I have a 1 over 3 to the n, so I have a 3 to the n in the denominator, and I have another 3 down here in the denominator. So I don't just have n 3's, I don't just have 3 times 3 times 3 n times, but one additional time on top of that. So it's really going to be minus 1 over 3 to the n plus 1. And that can be our sort of coefficient, if you will. And so this gives us a power series representation when it's all said and done. Or you could even, again, switch it. Usually we put the coefficient first, so maybe we should write it in this order instead. Again, neither one is a hugely important difference, but normally we write the coefficient, right, some a sub n times x to the n first. So here's our power series representation for this particular function. And we got to it by just algebraically manipulating this until it looked close to this. And then using our power series rules that allow us to basically substitute in one term for another, right? If I want 1 over 1 minus x over 3, 1 over 1 minus x over 3, it's going to be the exact same as the power series for 1 over 1 minus x, where everywhere that x shows up, I just swap it for x over 3. And again, this is only valid where the original function was going to be valid. So just keep in mind that because we combined both of these terms, this one had to be valid, absolute value of x had to be less than 1. This one required the absolute value of x over 3 to be less than 1. So in one case, we need the absolute value of x less than 1. The other one, we need the absolute value of x over 3 less than 1. And for the whole thing to work, we'll have to use whichever one of these is more restrictive. In that case, it's going to be this one. So absolute value of x less than 1. This one here is the equivalent of saying if we multiply both sides by 3, absolute value of x less than 3. So this is the more restrictive criteria, and that's the one that we wind up having to use. So this is, again, the more restrictive. Zoom in so you don't have to try to read. More restrictive criteria of the two. And so now that we kind of know how to generate a power series of new functions given older ones that we know, we'll use that as a jumping off point for looking at Taylor series, which we will finally introduce formally in the next video.